Good day, everyone. So today I'll give you an example on how to solve our PP diagram or air pressure diagram. So for this problem, we consider the FeO system at 298 Kelvin, wherein the species of interest are Fe, Fe2O3, Fe3O4, and FeCO3. Get the PP diagram if the following are given: the delta G naught for Fe, Fe2O3, Fe3O4, FeCO3, and also our gases of question, or the gases in our atmosphere, will be oxygen and carbon dioxide. So first step is to identify the species of interest. So in this case, the species of interest are itong apat na to: Fe, Fe2O3, Fe3O4, and FeCO3. Since there are four forms of Fe considered, which I'll just leave here: Fe, Fe2O3, have Fe3O4, and FeCO3, then there should be 6 couples. From our equation, number of couples is equal to 4 minus 1 times 4 over 2 is equal to 3 times 4 over 2. This is equal to 6. You can look at it manually. There's 1, 2, 3, 4, 5, 6. So there should be 6 couples or 6 equations that we need to consider. Now we have to get for the balanced chemical reactions between our 6 couples. So first, let's list yung ating anim. We have Fe2O3. We have Fe3O4. We have FeCO3. Have Fe2O3, Fe3O4, have Fe2O3, FeCO3, and we have Fe3O4, FeCO3. So mangyari dyan, Fe and Fe2O3, or there will be on either side of the equation. So we're transforming Fe to Fe2O3 and vice versa. And we need to balance the chemical reactions by using O2 and CO2 gas. So for the first one, we have Fe to Fe2O3, Fe to Fe2O3. We need to balance the number of Fe times 2. Then, meron tayong tatlong oxygen dito. Dapat maglagay rin tayo ng tatlong oxygen dito in the form of oxygen gas, which is O2. So, plus 3 halves O2. So, to continue on with the other ones, 3 Fe plus 2 O2 to form Fe3O4. I trust na marunong naman kayo mag-balance ng equations. So, now let's look at Fe and FeCO3. So, dito, we have the same amount of Fe. Now, we need to balance for carbon and oxygen. First, balancing for carbon, we need to add 1 carbon dioxide, since there's 1 carbon here, plus CO2. Then, if we look, meron pa tayong kulang na isang oxygen, 1 oxygen atom. So, we add 1 half O2. Now, let's continue on to the other forms of iron. So, we have Fe2O3 to Fe3O4. Kulang ka ng iron. So, we have we have 3 here, 2 here, 3, 6, 6, 9, and 8. So, kulang ka dito ng 1 half plus 1 half O2 for Fe2O3 and FeCO3. Fe2O3 to FeCO3. 2, kailangan dalawa yung iron mo, dalawa. Kulang ka ng carbon sa other side, nalagay ka ng dalawang carbon, plus 2 CO2. Count the number of oxygens, 1, 2, 3, 7, 1, 2, 3, 4, 5, 6, plus 1 half O2. For the last one, we have Fe3O4 plus form 3 FeCO3 to balance out the Fe. Kulang tayo ng 3 carbon here, plus 3 CO2 here. Then, count the number of oxygens. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. 9 plus 1/2 O2. We can then calculate for the delta G naught, or the standard free energy change for each of our reactions in the couples. So I'll just calculate the first one. It's we know delta G naught for the reaction, so in this case Fe2O3, it's just equal to the summation of the delta G naught of your products minus summation of the delta G naught of our reactants. So in this case, we have Fe2O3, Fe and O2 products, reactants. So for Fe2O3, delta G naught is negative 742.24 minus the reactants natin, this one and this one. You have 2 times 0 for Fe plus 3/2 times 0 for oxygen. If you calculate for this one, this will be equal to negative 742.24. This is kilojoules per mole. So we can get delta G naught for each of these expressions. I'll just list them here. This is negative 742.24. This is in kg per mole. Fe3O3 is negative 1015.46. FeCO3 is negative 272.34. Fe2O3, Fe3O4 is 195.8. The next one is 197.56. And the last one is 198.44. To be fair, it doesn't really matter whether we get whether we use itong form na to or baliktarin natin siya, as long as in delta G naught natin is this susunod yung kanyang sign. Since the aim of this exercise is to produce a pressure diagram, we usually in the pressure diagram, usually ang ginagamit natin is the logarithm of the partial pressure of one gas versus the logarithm of the partial pressure of the other gas. So in this case, where we want to plot the logarithm of the partial pressure of oxygen versus the logarithm of the partial pressure of CO2, it would be beneficial to us, or it would actually be essential for us to find this value. Why can't I have this? So we need to find yung ating log K. Yung log K natin, mula dun sa ating module, this will be equal to negative of delta G naught over 2.303 RT, where R is the gas constant and T is our temperature for this system. So our temperature here, I think, is at 298 Kelvin. So for the first one, we have Fe2O3. Delta G naught is equal to negative 742.24. We can get for log K. Log K is just equal to negative of 742 to 40. But since negative uli siya, may positive lang siya. So negative to, that's negative din yan. Over 2.303 times 8.314 times sa ating temperature, which is 298 Kelvin. If we solve for that one, we'll get 130. So log K will then be equal to log K equal to 130.08. And solving for the other ones, tabulate this. 178.00 have 47.74. The next one we have negative 34.32, negative 34.63, and we have negative 34.78. From the balanced chemical reaction, we can actually get an expression of log K with respect to log P and log P of O2 and log P of CO2. So let's look at these expressions. So we can build them from our equilibrium equation or from our equation here. So I'll probably this one and this one to illustrate. So for Fe2O3, ito, we know here, or I'll put it in the bottom just so I have space later. For Fe2O3, we know that KEQ will be equal to products over reactants, yung activity, which is activity of Fe2O3 over the activity of Fe squared times the activity of O2 raised to 3 halves. Condensed phase ng Fe and Fe2O3 natin is just equal to 1. Activity of a gas is partial pressure. So it'll be equal to 1 over P O2 raised to 3 halves. Getting the logarithm of this, we get log KEQ is equal to log of 1 PO2 raised to 3 halves. Para itaas to, magiging negative yung logarithm mo. So, become negative of logarithm of PO2 raised to 3 halves. A property of logarithm is that we can put this exponent into a coefficient at the outside of the logarithm. This will become negative 3 halves log PO2. From kanina, we have a value for log KEQ. Log KEQ is equal to 130.08. So this will be equal to 130.08. So we want to express our, we want to have an expression based on log PO2 and log CO2. So we can isolate log PO2 on one side. Log PO2 will then be equal to 130.08 divided by negative 3 halves. This will be equal to negative 86.74. Negative 86.74 is equal to log of PO2. We can also do the same treatment. Now let's look at itong number 3 natin, yung FeFeCO3. So for FeFeCO3, KEQ is equal to products of reactants activity of FeCO3 over activity of Fe, activity of CO2, activity of O2 raised to 1 half. This is again condensed phases 1 and 1. So we have CO2 and O2 na lang, which are partial pressures, equal to 1 over partial pressure of CO2 and partial pressure of O2 raised to 1 half. But we have log KEQ, so we have log here, and we make this logarithm as well. So in this case, para itaas to, magiging negative siya. Negative log PCO2 PO2 raised to 1 half. We know that pag meron tayong product here, we can add these two together. We would have negative log of P CO2 minus log of P O2 raised to 1 half. Yung 1 half natin, pwede natin siya ilabas such that log KEQ is equal to negative log of PCO2 minus 1/2 log of P oxygen. So log KEQ, we also have a value for this one. This is equal to 47.7385. So 47.7385 is equal to negative log PCO2 minus 1/2 log PO2. So for the sake of continuity, or para pare-pareho yung tignan sila, we isolate log PO2 in one side. So we have log PO2. So we move this here. It's equal to 47.7385 plus log PCO2. But since we move natin to negative 1, so meron pa tayong negative 1 dito, move natin siya dito, so become negative 2. Or log of PO2 will be equal to negative 95.46 minus 2 log PCO2. So we do this treatment for all of our equations. Yes, all of our equations, matrabaho siya. But mabilis lang naman siya, dapat. It's mechanical, but it's not really that hard. It's equal to negative 95.46 minus 2 log PCO2. So we do this for each of our components, or each of our couples, sorry. Negative 89.0002. Have log PO2 is equal to negative 68.6437. Log PO2 is equal to negative 69.26 plus 4 log PCO2. And lastly, we have log of PO2 would be equal to, for the Fe3O4 FeCO3 system, negative 69.569 plus 6 log PCO2. Now that we have the following equations for our different systems, yung ating log PO2 versus log PCO2, we now graph them in a line. We now graph them as a line, sorry. So in this case, what would happen here is that we take log PO2, this one as our y, and yung ating log PCO2 as x. So if log PO2 is equal to just some constant, this will become a horizontal line. So ito, horizontal lines lang siya. This one. Ito naman, slanted na line siya with slope. Kung ano yung coefficient ni log PCO2. So ito, negative 2 yung slope. Ito, 4 above and 6 pataas yung slope nito. So if we graph these lines, we'll get something like this. So looking back, first, we have Fe2O3. Its log PO2 is equal to negative 86.74. It's this one. Fe2O3, negative 86.74. Ito yan. Straight line siya, y is equal to something. So for yung mga straight lines natin is ito. We have Fe3O4, negative 89.002, and log and Fe2O3, Fe3O4, which is negative 68.6437. This one, and this one here. Now, to know which would be above and which would be below, we need to analyze our equation and determine kung paano yung flow ng ating products and reactants depending on the partial pressure in our system. So in this case, let's look at Fe3O4 here. yung equation ng Fe3O4 natin, if we look at this one, we have Fe to Fe3O4. This is tatlong Fe plus dalawang oxygen. So, mangyayari is if we increase our oxygen content, this actually corresponds to going up here in the log PO2. If we increase our oxygen content, by Le Chatelier's principle, what would happen is the system would compensate towards the production of more Fe3O4. So above the line, this will become more Fe3O4 here. Kasi pag tinaas natin yung oxygen, mas likely na mag-form si Fe3O4. And in the opposite case, pag binabaan natin yung oxygen natin, kulang na siya dito. So what would happen to compensate for the equilibrium being lost is Fe3O4 will turn back into Fe to form more oxygen gas. So if you recall your Le Chatelier's principle. So Fe would be below. So applying that analysis, we can get the following. Fe sa baba, Fe3O4, and so on and so forth. Now for the slanted lines, we have FeFeCO3, negative 2 log PCO2, log PO2. This is this one, pababa. We have Fe2O3, FeCO3, log PO2, 4 log PCO2. So I'll just graph this. I used Excel to graph, and Fe3O4, FeCO3, ito siya. Now that we have plotted our equilibrium lines, it is now time for us to do the most important step of the exercise, and probably the hardest part. We now have to determine the stability regions of our species. The domain of thermodynamic stability for each individual species is determined by requiring that all of our equations involving the said species be satisfied simultaneously, or we have to solve multiple equations involving that species at the same time. So, essentially, ang gagawin natin is solve natin lahat ng equations natin ng sabay-sabay, which is a tad difficult to do. So, for our purposes, we can cheat it a little bit, cheat in quotation marks, and exploit some rules for the triple points, or points where our lines intersect. So, an example of a triple point in our diagram is this one, and this one. These are possible triple points for our diagram. So, for our triple point, first thing is to know is that lines around our triple point will alternate between being stable and metastable, or another fancy term for unstable. Stable, unstable, stable, unstable. So around that, pwede maging ganyan siya, or the opposite can be true. Pwede ganyan, unstable, unstable, stable, unstable. Pwede siya maging ganyan. Another thing is that when a stable line passes through a triple point as so, it will become unstable after. It's just a corollary or a consequence of the first rule. Another thing we consider is that the stability regions are bounded by equilibrium lines containing that species. So we can know if our assumption would be correct, or if our diagram is correct, if the equilibrium lines are bounding the stability regions that we have proposed. So we can use the principles that I've just said in order to arrive to the equilibrium diagram by using TAE method. So that is your trial and error method. To do the method, first, we assume that we have a stable line. So our stable line is one that is connected to our triple point. So for the sake of this exercise, I will say that the stable line would be this one. So until the triple point, it will be stable. So if that is the case, from our triple point rule, yung next line will be unstable if we go around the triple point. This would be stable, not stable, stable, till triple point, so stable, and not stable. So makita natin itong line na to, this actually extends until the next triple point, as shown here. Parang ganyan siya. Or let's just make with it this. It's like this. It's unstable, so on. So now we arrive to another triple point. So we just do the rotation again. Stable, not stable, stable, not stable, stable, and this one would be not stable. So in this case, we have ito. So we would have these stability domains. Now, to know if our assumption is correct or kung ano yung nandito sa stability regions na to, we now look at the equilibrium lines kung paano nagbabound tong region na to. So for the bottom part, we know that it is enclosed by an FE-FE304 equilibrium line, and sa baba ng equilibrium na ito, dapat FE daw siya. Itong line na to, we have FeCO3 and sa baba is Fe. So we see na parehong Fe, 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 Fe. So parehong Fe yan, then this should be Fe. Now let's go here. Sa taas na to, Fe304 daw siya. Itong line na to, Fe304 here. So this would be Fe304. And sa baba na itong line na to, this is Fe304. So this should be Fe304. Taas nito, Fe2O3. Itong line na to, Fe2O3 sa taas. So this would be Fe2O3. And lastly, ito, FeCO3 sa taas. Fe3O4, FeCO3 sa baba. And this one, Fe2O3, FeCO3 sa baba. So ito, bounded siya by FeCO3, FeCO3, and FeCO3. So this will become FeCO3. Looks something like that one. So I'll just pretty this up a bit. Oh no. So we would have this equilibrium diagram. So we have Fe at the bottom, FeCO3 at the right, Fe3O4 dito sa middle, and Fe2O3 dito sa taas. But what if we assumed a wrong line? So let's try doing that. What if instead of this line, we use this line? So if we did that, oh no. If we did that, we would have ito, 1. So this is unstable. See stable. This will become unstable. This would be stable, and this one will be unstable. So ito is upon triple point. We would have ito. This one will be unstable. This would be stable until here. This will become unstable. This one will be stable. And so on. So this would be our current stability region. So ito na wala yung triple point mo since ito na tanggal na siya. So what would happen here is we determine again if this makes sense. So sa una pa lang makita natin this won't make sense. So since ito, if tinignan natin yung bottom, mangyayari dito is sa baba nito, this would be Fe. Sa baba nito, Fe. But sa taas nito is Fe3O4. So hindi natin alam kung ano ba talaga ito, Fe or Fe3O4, which means this assumption would be wrong. So using the trial and error method, we actually can only get one. We can only get the right answer if nag-correspond lahat ng ginawa natin. Kung tama yung ginawa natin, isa lang dapat yung makakuha nyo. If makita natin na bounded data stability regions by equilibrium lines, na that makes sense. So there's only one answer, and the trial and error method can get you to that answer. And that answer would look something like, hopefully, like this. So hopefully, you got how to do this. So for the next video, I'll make something naman to solve for our Porbay diagram. So thank you and have a nice day. Good luck. Bye-bye.